Okay, so today we're going to do nets, but first we need to finish off our discussion of local compactness. And so recall last time we saw how locally compact Hausdorff spaces are actually pretty nice spaces. We showed that if a space is locally compact Hausdorff, if and only if there exists this one-point compactification. So that's quite nice. And then the last thing we looked at was for a Hausdorff space, we can use as a definition of locally compact the fact that if you're given a point in the space and a neighborhood, then there is a neighborhood of that point inside that neighborhood such that its closure is compact. And so that's kind of like a more what we would think of as a local definition. Okay, and so we just needed to finish up a few corollaries then of that. So if we've got a locally compact Hausdorff space and we've got a subspace of that, then if we have a closed space or an open space, then that's also going to be locally compact. And that follows pretty straightforwardly. Say we have a closed space. We want to show that A is locally compact. So given a point in our closed space, then if we take a compact neighborhood containing a neighborhood U of that point in X, right? Remember, because X is locally compact, we can do that. Then the intersection of our compact subspace with this closed space is going to be compact, and it contains a neighborhood of A, which is just U intersected with A. So that's pretty straightforward. And if A is open, right, then this is actually the point which is actually really the corollary of 29.2. If A is open, then for any point in A, by the previous theorem, we have a neighborhood of V of X such as its closure is compact and that its closure is contained in the neighborhood. And so then that just follows straight away. And then finally, a space is homeomorphic to an open subspace of a compact Hausdorff space. And this is really a useful corollary because what we can do, right, if we've got a space that we're studying and we can show that it's homeomorphic to a open subspace of some compact Hausdorff space itself, then it's locally compact Hausdorff. All the stuff in with the one-point compactification. Okay, and so that follows straight away from 29.1 in this direction. It follows from that one-point compactification, and in this direction, the fact that if it is an open space subspace, then it's locally compact. That follows straight from 29.3. Okay. So the key message is that locally compact Hausdorff spaces are pretty amenable to a lot of techniques. Okay. So the main thing I wanted to talk about today is nets. So what is a net? So I have to warn you that at first it'll seem a bit kind of like abstract nonsense. It's kind of, we're generalizing the concept of a sequence, and you might think, well, isn't this kind of generalization for generalization's sake? And the answer is no. And I'll go right to the last slide about this theorem that shows that a space is compact if and only every net has a convergent subnet, right? So a net, remember, is the generalization of a sequence. A subnet is a generalization of a subsequence. So this shows that we can use as a definition of compactness that Bolzano-Weierstrass kind of property that we sort of saw before didn't work if we were just talking about usual sequences, but it does work if we then generalize what our concept of a sequence is. So this theorem actually tells us that when we're talking about nets, we're actually talking about something real and deep, because then it shows us that really we can think of compact spaces as having this Bolzano-Weierstrass property for nets, which is kind of what they first wanted to do in the 19th century. But we saw that sequentially compact is not the same thing as compact. It is when we've got a metric space, but this shows you, okay. And so it gives you some sort of justification in defining nets. Okay, so let's start. So the first thing we have to talk about is, remember the idea of a partial order. So the standard idea of a partial order, it's kind of different from the orders that we did before, like the simple orders that we did before, because there we're kind of used to any two items, any two elements being able to be compared to each other. Okay, but it's possible to have a partial, to have an order in which it's impossible to actually compare two things. So a partial order is an order which is a relation which is reflexive. So something is always less than or equal to itself. It's anti-symmetric. So we've got alpha less than or equal to b and beta less than or equal to alpha, then alpha equals beta. And the transitive property, right? So alpha is less than or equal to beta, beta less than or equal to gamma, then alpha is less than or equal to gamma. Okay. So one way to think about this is like just a normal less than or equal to for numbers, right? As distinct from a strict partial order, right? So when we talk about strict partial orders, we don't have the anti-symmetric quantity in there. So then, when we have a partially ordered set or a PO set, you might have heard it being called, that leads then to the idea of a directed set. So a directed set is a partial order such that any two elements has an upper bound. Okay, so what does that mean? So that means if I give you any alpha and beta in our set, there has to exist a gamma such that gamma is greater than or equal to alpha and beta.
So each alpha and beta, or when you pick any two pairs, they share some common upper bound.
So yeah, so any two elements have a common upper bound. Exactly. So we've got some examples there, so that might answer that question. So a directed set is a generalization of a simply ordered set. Okay, and some definitions of a directed set omit the anti-symmetric thing. So some people think that for a directed set, you don't need this property that if alpha is less than or equal to beta and beta is less than or equal to alpha, it doesn't necessarily have to be that alpha equals beta. So for example, it's quite easy to come up with an example. Say your set J is the set of neighborhoods of 0. And let's say that U is less than or equal to V if every ball centered at 0 radius epsilon in U is also in V. Okay, then it's possible for it's possible to have like a set. So if we have a set like this, so here's 0 here, and if we let sort of U be this, and V be this, right? Then in both cases, the biggest ball centering 0 is some epsilon, and it's the same epsilon. So U would be less than or equal to V, V would be less than or equal to U, but they're not equal. So some people allow that to happen. Okay, so what are some examples of simply ordered set, of a directed set? So as I said, it's a generalization of the simply ordered set. So any simply ordered set is also a directed set, right? Because what happens if we're given any alpha and beta in our simply ordered set, then one has to be greater than the other, and that one is then an upper bound for the two elements. So it's trivially directed. And so, as I said, we're going to generalize the idea of sequences. So directed sets are what we're going to do to generalize the indexing of our sequences. So typically we have Z plus, the positive integers, which is going to index our sequences. That's an example of a simply ordered set. So now our sequences, we're going to be indexed by any directed set. So let's have a look at a few more. So what was your question, Will, before?
Right. Like that any virtual work would have that property.
That it would have an upper bound? No, because if you had a set, if you had a relation that kind of looked like that, like an upside down tree, for example, and it just kept on going forever, anything on different branches wouldn't, it'd have to be in the same branch to be able to be compared. So no. Whereas, of course, if it was the tree went the other way, then it would have an upper bound. So this is called this is a Hasse diagram. Have you heard of those kind of things? So this is like the diagram which gives the relation in the pose set.
So it's the lack of
Yeah. Exactly. So whenever you check that something is a directed set, you've got to be able to check that comparability. So that's basically what then, in these last three examples, we'd have to to check. So let's have, so the collection of all subsets of a set partially ordered by inclusion is a directed set, right? And so if you're given two subsets of S, alpha and beta, what's going to be the upper bound of them?
Easy plus.
Hmm?
Easy plus, like, I didn't think here.
So in three, so here our ordered set is the collection of all subsets of a set, the power set of a set.
So it will be like our big set. Like,
And so we've got some set S, right? And J we're going to have as the power set
yeah,
of S.
S will be the upper bound.
S is an upper bound, but in fact you've got a least upper bound. A union, yeah, just the union would be that. Okay. And example 4. So for us, actually, we're actually going to be more interested in reverse inclusion, because if you think about it, you want your sequences to kind of narrow in on something. So reverse inclusion is much neater. So let's say a collection of subsets that is closed under finite intersections, i.e. open sets, for example. Partially ordered by reverse inclusion. Okay, and so now if I have alpha and beta element of our collection, what is an upper bound for that? The intersection, yeah, exactly. A intersection beta. It's included in both of these. So since it's reverse inclusion, they're greater than they're greater than alpha and beta. And then it's the same thing for 5, the collection of all closed subsets of a space partially ordered by inclusion. And again, intersection is going to work because the intersection of any two closed sets is closed. Okay. So it's these kinds of things that are going to be useful when it comes to defining a sequence, generalizing a sequence. Okay. The next concept is cofinal, and this generalizes the concept of the subsequence. If you think that's too fancy a word, another word that's used to measure the same thing is frequent, or set frequent is the same thing as cofinal. So a subset of a directed set is called cofinal if for each element in J there's an upper bound in the cofinal set. Okay. And if you think about it, this does kind of generalize the concept of a subsequence, right? So it means that, like, for example, if you had x1, x2, xn, blah, 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 then your subsequence would be xn1, xn2, etc. And the point is then that anything here, there would be something in the subsequence which would be further on. So it's just saying that the subsequence sort of goes to the same place that the sequence goes to. Okay, and so for this to work, we need the following result, that if J is a directed set and K is cofinal in J, then K is a directed set. Okay, now why is that? So what are we going to show that it's a directed set? So we've got alpha and beta in K. What do we want to show? We have to show that there exists an upper bound in K.
For alpha for each of them, there is an upper bound, right?
Right, so alpha and beta are also elements of J.
So there exists like upper bound for both of them.
So there exists an upper bound, let's call it delta, which is in J. For that, then how do we get an upper bound in K?
Because it's in J2, it's in J2, so for delta 2, we have an upper bound.
Because K is cofinal then, so since there's cofinal, there exists our gamma then in K such that delta is less than or equal to gamma, but alpha is less than or equal to gamma, so by transitivity, it works for those elements alpha and beta. Okay. Excellent. So here's the idea of a net then. So this is what we're going to do to generalize the notion of a sequence. And this gives us the same definition of it as a sequence that we're used to if we take the directed set to be the positive integers. Okay, so X is a topological space. A net is a function from a directed set into X. And so usually we denote f of alpha, some index, by X sub that index. And we denote the symbol, we denote the net f by a symbol sort of denoting that it's a sequence, right? So either we put the set J explicitly there, or if we don't worry, if there's no confusion about what J is, we leave it there. Then, what does it mean to converge then? So a net converges to a point, and we write that as like typical convergence notation, X alpha goes to X. If for each neighborhood U of X, there exists an alpha in our directed set, such that whenever beta is greater than or equal to our alpha, X beta is in that neighborhood.
We are talking about, it says it's a function of topological space, but are we talking about open sets or just elements of a topological set?
So U is an open set because it's a neighborhood.
But from direct set, we're mapping to the elements or open sets.
We're putting into an element. Okay. So f is a function from J to X. So f of alpha is an actual point in X.
Because sometimes, like in a book, they use topological space, and actually they're talking about open sets, not exactly.
Right. So quite often, what's going to happen is alpha is going to be an open set or some neighborhood, and so this is going to be some point in that open set. Now, why is that the usual definition? Well, let's just replace J by positive integers. So remember, a sequence in X is a function from the positive integers into X. And so if n is a positive integer, we denote f of n by x sub n. We denote the sequence by this symbol, right? You put brackets, and we say that a sequence converges to X, and we write it like x sub n goes to X. If for every neighborhood U of X, there exists an integer, usually say big N, such that whenever little n is bigger than or equal to big N, xn is anything. So it's exactly the same concept as the sequence that we had before. Okay, so it all fits in with previous concepts. So it works well with products, Hausdorffness, closure, and continuous functions. Okay, so let's sort of go there then. Okay, so if we have a net in x going to some little x and a net in y going to some little y, why do we get a net going to x cross little y in big X cross y? Well, we just look at, you just use the definition. Right, so what is our net going to be? So our net is going to be a function from our directed set J into X cross Y, where f of alpha is going to go to X of alpha cross little y of alpha. Okay, so the idea is well defined. Why does it converge? Okay, so what can we say? Why is little x cross little y what this sequence this net converge to? Well, what do? We choose some neighborhood. So we can kind of use a basis element, a neighborhood, the basis element cross B, right? And then the fact that X alpha converges to X means that there is alpha such that X beta is in U when beta is bigger than our alpha, all right? And the fact that Y alpha goes to Y, I should start using different indexes, means there is a gamma such that Y gamma is in V when going to put the
And that's
hang on, I'm getting indexed out here. I want to say, where's my delta? I want to use delta and gamma. So let's use delta here. There is a gamma whenever delta is bigger than gamma. Okay, and so that means X beta cross Y beta is going to be in U cross B whenever beta is greater than or equal to the upper bound of alpha and gamma. I don't know if I've done this correctly, but we know for U and for U there is an element of J such that all the elements are going to be in U for the index greater than beta, and it's going to be in V whenever the indexes are greater than gamma. So we just look at the upper bound of alpha and gamma. It doesn't have to be. Remember, they don't have to be comparable directly, but there is an upper bound. So whatever that upper bound is, then this set here is going to be in this neighborhood here. that okay? I've done that okay?
I didn't get why did not jumping to like product set? How can you just say okay now I find that
Right, so we've got a sequence which goes, we've got a sequence that goes in each space, and we can construct a sequence that goes into the product space. We're just doing each component wise. What about Hausdorffness? If X is Hausdorff, then a net converges to at most one point. So we've already seen this, this lemma for sequences. Okay, so how would the proof go? So what would we assume? So let's assume by contradiction. So let's say a net converges to 2 points. Exactly. So now we need use the Hausdorffness. So let's say X alpha converges to X1 and X alpha converges to X2. So if X1 doesn't equal X2, that means by Hausdorff, there exists disjoint neighborhoods U1 and U2, such that what? So the intersection is empty, but the fact that X alpha goes, so maybe I should use different, let me use different things there just to, so I don't. So what happens here? So that means what? So the definition of convergence means there exists an alpha such that X gamma, I'm going to start trying to be careful with my indexes here, such that X gamma is in U1 whenever gamma is bigger than alpha. What else? There exists something else. Let's say call it beta. There exists a beta such that X delta is in U2 whenever delta is greater than beta. Okay, what's the next line of the proof?
Now we have the max of them.
Right, so now, so there exists an upper bound. What do we call it now? We need something, yeah, we need a new letter epsilon, such that X, what's after epsilon? It's a nu, such that X nu is an element of U1 and U2 whenever when mu is less than epsilon. Yeah. And that's our contradiction. Okay, so that's the kind of games you have to play with directed sets. So you'll notice though that every time we do this, in all these proofs, we never use anti-symmetry. So when we go back here, we only ever use properties 1 and 3 of the partial order. So this concept of a net does not need anti-symmetry. So we can yeah, we can do that.
I like in real analysis, we use anti-symmetry a lot, but it's like when you're doing real analysis with sequences. For example, like when we want to prove that something converges to something, that something equal to something, we just prove by anti-symmetry a lot.
Okay. You don't seem to need that here. Okay. Next one, which is that's another thing that we want sequences that we want our nets, property that we want nets to have to kind of mimic what sequences have. Then if we have any subspace of X, then X is in the closure of A if and only if there's a net of points of A converging to X. That means we've actually got to come up with we've actually got to construct a net of points. So let's say, let's go this way first. Let's say X is in the closure of A. And so what we're going to take then for our directed set to be neighborhoods of X partially ordered by inverse inclusion. Right, so a neighborhood is bigger than another neighborhood if it's included inside. Okay, and we've already seen that this is a directed set. And so what's the net that we're going to take? So that we have to come up with a net. The net is going to be a function from J to we want it to A, right? Because it has to be a net in A. And so let's just take F of alpha is an element of A is just some element then of alpha.
Smaller, right?
Right, so it's smaller and smaller, so we're more restricting that to it. So I don't know if we're using axiom of choice here, but we're just assuming that we can do that, so we're not going to worry about that. So we're just going to choose some point in alpha, distinct, of course, from X. So we're not going to, of course, if X was in A, it'd be trivial, right? Because the constant net would stay within X and that would converge to X. So it's only if X is in the closure minus A that we actually have to do anything. So this is no problem. So what do we have to show? We have to show that this net then converges we want to show that X alpha converges to X. Okay, so what do we have? So for each neighborhood of X, let's say for each neighborhood U of X, well, U is actually an element of J. And then for each beta, which is bigger than U, we have beta is actually included inside U. So since X sub beta is an element of beta, then X sub beta is an element of U. So that's exactly what we need for the definition of convergence. And then going in the other direction, if there's a net of points converging to X, then just by just looking at this, then we see that each neighborhood then of X intersects A. And so that's the definition of being in the closure. So that theorem works. I think we've got time for the last theorem on this slide. The other thing, of course, we want a net to have is it have the same properties as a sequence does for continuous functions. That a function is continuous if and only if for every convergent net, we get a net in Y which converges to f of X. So how do we go about doing that? So what do we need? We need then that the inverse. So if this is true, then we want to show. So what do we want to do? So we want to show. So this is actually being continuous at X. So this is continuous. So f is continuous. That this is true for any point X in a little x in X. So what are we going to do? So what are we going to do? We've got to show the inverse image of open sets is open sets.
We want to use the local continuity.
The local continuity. What? So which one's that?
I don't know. It just seemed like the other statement here that we get the
Yes. Okay. Yeah, I think you're right. Although one direction we already got, don't we? So if this is true, then this has to be true. because in particular, it's true for sequences, and we've already proved that. Okay, so the only thing we have to prove that if f is continuous, then this is true. Okay. So we use the fact that f is continuous. So if f is continuous, any neighborhood of f of x, its pre-image is going to be a neighborhood of x. So that, right, so so it's actually going to be the same index that's going to work in the same, for the same net. So f is continuous. So here we've got a conversion. So what we've got f is continuous, and we've got x alpha goes to x. So we want to show that f of x alpha goes to f of x. Right, so we want to show that given any neighborhood of f of x, there exists an alpha such that f of x alpha lies within that neighborhood. And that's going to be true then, because when we pull it back to here, any neighborhood of x is going to have x alpha in the pre-image of that neighborhood, and it's going to be the same index that's going to work for both cases. So I think that works. Yay. And so the final thing is then that we've got a the idea of a subsequence. So if we've got a net, and then we've got, which is given as the directed set J as its sort of index set. And so then if we've got another directed set K, such that we've got a function from K to J, such that whenever I is less than J in K, G of I is less than or equal to G of J in J. So this is the same kind of concept of taking a subsequence, where when you take a subsequence, you're just taking only particular parts of the sequence. And this is just saying that you're keeping the same order. So the subsequence, in the subsequence, things that are in the same order there are in the same order as in the sequence. And you want it to be cofinal in J. That the image of K is cofinal in J. Right, so that means you've always got this upper bit. So that's going to be a directed set.
You want it to be cofinal so that it will converge eventually.
Exactly. So that you have this lemma here, that any net that converges to X, so there's any subnet. And so this composition then of F composed with G, so that gives you then a map from the directed set K to X, and that's a subnet of X alpha. And so this thing here is what you need then to make sure that if X alpha converges to X, then so does any subnet, right? Because what does that mean? So X alpha goes to X means that there's some index such that the X alpha is going to be in that neighborhood whenever alpha whenever your index is greater than an alpha, or for the subnet, right, because it's cofinal, it's also going to have the same property that there's going to be some upper bound that such whenever elements in K are bigger than that, that's also going to be in that same thing. And that's going to happen because it happens in J. G of K is cofinal in J, so that means there's something in G of K which is bigger than that thing there. And so everything in that subnet is going to be in that neighborhood then whenever it's bigger than that. Okay, I think that's where I'll stop. Right, and that's the only thing that I had left.
For subnet, if you just say instead of like second axiom in definition, you just say everything to converge, it will necessarily will be in that profile, right? For example,
you don't want to make sure that you want to make sure that it actually goes. So,
for
like,
example, what I'm saying is I can exchange to this conversion. Who end up being this like profile anyway, because if everything should converge means that for each band there is an upper bound.
okay, so you're saying that you want to swap these two?
Yes.
I don't like that because
It's more obvious and easier.
so if you like, you can think of this lemma as a definition you like, but it is I think it logically proceeds as a lemma from an axiom. Okay. So next week we're going to start on an entirely new chapter. We're going to start looking at different. We're going to put away compactness for a while and look at other topics.
Why not introduce sequences and nets together? You know what I mean?
So